In this video, we're going to talk about diffusion and osmosis. Let's start out by talking about diffusion. Diffusion is the net movement of molecules from an area of high concentration to an area of low concentration until that net movement evens out. Let's take a look at some examples. Let's say you walk into Starbucks and you start to smell the coffee from across the room. Or you walk outside and someone is cutting the grass and you can smell that fresh cut grass. Now, diffusion is not just in the air. You can also see diffusion in water. Let's say you want to make yourself a cup of tea. Now, there are certain factors that do affect the rate of diffusion. Using hot water instead of cold water would affect making tea. You're going to make tea a lot quicker. The rate of diffusion is going to be faster in hot water and high temperatures than if you had cold water. The other things that are going to affect it is distance, right? So let's say you have a very small teacup. You would have the rate of diffusion much quicker than if you had a very large teacup. Other things that affect the rate of diffusion include the mass, include density, and also include whether or not that solvent is moving across a barrier, such as a semi-permeable membrane. All right, let's start talking about osmosis. Osmosis is very similar to diffusion, except this is the net movement of water, so H2O, from an area of low solute concentration to an area of high solute concentration. You can also say that this is the same thing as an area of high water concentration to an area of low water concentration until that net movement evens out. This is also always going to happen in water through a semi-permeable membrane. Let's go through some examples. Okay, so let's say you are looking at a cell that, let's quickly go through. Let's say you are looking at animal cells, and this is your test tube, and we have blood in here. So let's put some blood cells. And we're going to see how the blood reacts to 3 different solutions. Let's say we first are going to put into our test tube a hypertonic solution. Okay. That simply means that the solution that's being added to your red blood cells has a higher concentration, a higher solute concentration than your red blood cells. Which way would the water go? Let's pull out one of these blood cells. Okay. And remember that you have high solute concentration on the outside. So this would be low solute. And this would be low water. Whereas this would have, if it's a lower solute, it would have a higher water concentration. Which way would the water go? The water would go from an area of high water concentration to an area of low water concentration, or an area of low solute concentration to an area of high solute concentration until it evened out. And this would cause the cell to shrink or crenate. And so you would almost have like this star pattern. All right, next example. Let's say instead of a hypertonic solution, we are going to now add a hypotonic solution. Hypotonic solution. Okay, what would happen to the cell? Now, an example of a hypotonic solution would be water. All right, so let's say we added water to our red blood cells. We have a higher solute concentration on the inside, so this would be low solute concentration. This would be high water, and this would be low water. What would happen? Water would rush into that cell. If this is a plant cell, it wouldn't be an issue. Plant cells have cell walls, and so they can hold up to that pressure. But unfortunately, with a red blood cell, if you were to inject somebody with water, their cells would burst. Okay, last example. Let's say you are at the hospital and you are getting IV fluids. Now, they're not pumping you full of water. They are pumping you with an isotonic solution. And this is 0.9% NaCl. And so if you put an isotonic solution into your red blood cells, you're going to have a even net movement in and out of that cell. You're not going to have any shrinking, and you're not going to have any swelling or bursting. I hope this helps.